this is 125, and so there was no class 2 weeks ago. That was the college meetings day, so here's the last, we did part of Chapter 4, and today we're going to do the rest of Chapter 4, which is the Net Plus chapter, the basic networking. So, wireless area networks. One very common problem with wireless networks is denial of service. This happens all the time, often just from accidental interference with other wireless signals or motors and such. You can also launch an attack by sending deauth frames, which will disconnect everybody, and there is currently no known defense against this. Now, there are bands available for limited bands of wavelength are available for general use. Most bands have been sold for a specific purpose and you can't use it for anything else. So a lot of bands, a lot of traffic, a lot of devices are all sharing two bands, the 2.4 gigahertz and the 5 gigahertz band, which is why you get so much interference. Now, frequency hopping spread spectrum hops across many channels. Direct sequence spread spectrum also uses a lot of channels. And orthogonal frequency division multiplexing is a way to send multiple streams of data at the same time by carefully choosing radio signals that will not interfere with each other and be kept separate. So the various Wi-Fi generations, it started with the early Wi-Fi 802.11b is the one that went around, that in the 2.4 gigahertz band that only went up to 11 megabits per second. Then we had 802.11g, and N became popular. Now a lot of people are using Wi-Fi 6 and Wi-Fi 7, and they're getting really fast. This one, Wi-Fi 7 supposedly goes up to 40 gigabits per second. I'm using Wi-Fi 6 at home, and it's plenty fast. I'm getting 600 or 800 megs out of it. So anyway, like everything else, it keeps speeding up. So there's 4 modes of a wireless network card. Normally, the only one you use is the managed mode, where the card connects to an access point and the access point tells it what to do. That's normally the only one you use. These others are only used in special cases. So managed mode is the normal one. Your card is a client. This is what's in your laptop. It connects to an access point, and the access point tells it what encryption to use, what channel to use, and so on. Master mode is what the access point is using. It is the boss and tells clients what to do. So that makes sense. Ad hoc mode is for peer-to-peer networks with no access point. And you could have 2 laptops and no access point, and you could connect them one to another like a crossover cable with no internet. I don't think I've ever done this, but in principle it's possible. Monitor mode is the one I've used quite a lot. Now, when you are on a network of any kind, a layer 2 network, your device has a MAC address, and you often receive packets that are for some other MAC address. If you're on a switched wired network, this doesn't happen very much because the switch is intelligent and only sends you packets, only sends you frames with your MAC address. But if you're on a wireless network, you get all the traffic within line of sight, and that's a lot of traffic that's not intended for your NIC. So your network interface card typically discards all the packets that don't match your MAC address, and they never even enter higher levels of the computer. But if you turn on monitor mode, it will pass all the traffic through, so you can examine packets that were sent to a different device, which is not something you would normally do for any legitimate purpose. It's mostly because you're trying to spy on people, but it could be you're trying to just record all the traffic as part of a network security process. So the SSID is the name of your network that appears here. This is broadcast by the access point. Some people recommend disabling this so you don't appear in this list, and therefore casual users won't find you. Now, a user that sniffs packets from someone who connected would still be able to find the SSID, so it's not a very strong security measure, but it will probably stop casual people from just connecting to your network. But of course, if you don't want that, what's much better is to put on a password with WPA or WPA2 or 3, and then even though they can see you, they can't get in without the password. MAC address filtering is another weak process. You can only let certain MAC addresses connect. I used to do this when I had a weak access point on my phone and it couldn't handle the encryption very well, so I just used MAC address filtering. Now, in principle, a sophisticated attacker could turn on monitor mode, sniff the packets, and find out the MAC address of the authorized client and get in. But again, a casual user that just looks at this and clicks on it won't be able to get in because they don't have the right MAC address. So another weak security measure. WEP was the original encryption measure intended, came out with 802.11b, and they tried to tell people, when they tried to sell wireless NICs in the 90s, customers were worried. They said, this seems unsafe. Seems like my data is going all over the place. And if I had a cable, it would only go down the cable, and that is all true. So they've turned on WEP, which was intended to make it as secure as a wired network, but it was a poorly designed protocol with many security flaws, and you can crack into it without knowing the key very easily. So it's all pretty much extinct now. There's some old devices still using WEP, but it's not considered secure enough for modern use. So 802.11i came out that defined WPA2, Wi-Fi protected access. And this is the one most people are using now, AES encryption and something called CCMP, which is another thing, which makes another cryptographic system that means people can't get in if they don't know the password. WPA was a transition intended to make WEP more secure. It really is just WEP, but it keeps changing the key frequently, and that made it more secure than WEP, and turned out to be pretty successful. But it was designed to be just a software update on routers that had been designed for WEP. So you didn't need a new hardware for it. And so that was the plan. And it was much better than WEP for a while. Very few people are using it anymore. They're mostly on WPA2 or even WPA3. All versions of WPA are quite secure, though. In general, there's no way to get in any of them without the key, although there are a couple of extravagant attacks that get you some very limited information about the traffic, but nothing to worry about very much. Bluetooth, on the other hand, has a lot of serious security flaws. Been around for a long time, many different versions running at different speeds, and it uses a symmetric stream cipher, but they found that it's weak, and devices, hackers can get in, and there's a lot of attacks, especially on Bluetooth low energy. There's quite a few attacks that come out. RFID is these tags you put on objects so they can be detected, scanned. This is in modern credit cards. You mostly just wave the card at the terminal. You don't plug it in or anything. And this is a short-range radio identity. The tags are used to pay your toll if you go over the bridges around here are RFID tags. The active tag has a battery. Semi-passive has a battery too, but the passive is the most common. No battery. It's powered by the reader. It has an antenna that picks up a signal from the reader, and that's enough to power the chip to do a exchange. And it's got a cryptographic, it's not just memorized data like a mag strip, it does some kind of cryptographic calculation, so you can't easily clone one. Yeah?
Excuse me, these are opposite of what radio frequency identification,
Yeah.
These short form of first capital of the word, what is that?
Yeah, this is the way they abbreviate it, RFID, radio frequency identification.
No, I know that. D is the part of the which word? Such as identification, radio, frequency, F, identification, I, and B, what's...
Because ID is a common abbreviation for identification.
That's
yeah.
ID.
Yeah, that's the idea. Yeah, it's a good question. There isn't any... No, there's no D. That's a good question. This is fairly common. This is fairly common that these acronyms are not really one-to-one. That's just unfortunate. These acronyms, English majors hate these acronyms for this reason. They're not very systematic. They often do things like take two words, two letters, sometimes even not sequential letters. Yeah, these are really like slang, but they're what people use. Yeah. And so, anyway, if you want to block radio signals, you can just surround your device with several layers of tinfoil or a wire cage. And people make rooms that just have metal in the walls and metal in the floors, and then you have a radio dead zone. There's several of these. There's one of the colleges I teach at, the classroom is a dead zone. I can't get any internet or Wi-Fi in there. Anyway, that's a Faraday cage, they call it. All right, so let's try a Kahoot. Should have them here. 4G, here we are. All right. Oh, that's not how you do it. 4G host live. There we go. All right. All right, so what mode connects two devices together like a crossover cable? That's ad hoc mode. Okay. All right. Which technology uses transmissions that do not interfere with each other? Yep, those are orthogonal frequency division multiplexing. They call the transmissions orthogonal because they don't interfere with each other. All right, which standard uses only 5 gigahertz? It was A. I think G uses both. Let's go back and check that. Yeah, G uses both. No, G is 2.4. Oh, that's right. A uses 5 only. Yeah. And, okay. It was A and N and, but wait, G. Oh, G was 5 gigahertz? No, G was 2.4. Okay. And N was both. Okay, fair enough. So I think it's right. All right, that's A. All right. And how do you block a radio signal? Yep, you put a grounded cage around, and that will stop the radio from getting through. So, secure network devices and protocols. So at layer 1, you have cables, and repeaters work at layer 1. The repeaters just receive traffic on one port and just repeat it out the next other port, and the only point is to boost up the signal because the electrical signal attenuates fit distance. A hub is a multi-port repeater. Everything that comes in, every port in the hub is just repeated out every other port. It doesn't interpret the signal at all. It just repeats it out the other port, doesn't read addresses or make any decisions about it. And it cannot send and receive simultaneously. And this creates a collision domain. If two devices try to send at the same time, the electrical signals collide and create invalid data. So bridges have 2 ports, and the purpose of them is to connect 2 network segments together, and the bridge will learn which MAC addresses are on this side and which MAC addresses are on that side, and it will only send traffic in the correct way. And so a switch is a multi-port bridge, and this is what most people use now. Each port, it has intelligence in here, it has memory, it has a computer, it keeps a switching table. It learns which MAC addresses are on every wire and only sends data down the correct wire to reach that MAC address. So essentially ends all collisions. And trunks are lines that connect multiple switches. So VLANs are virtual local area networks where you can specify that broadcasts should only go over a certain range here. And so you can, even though in the original switches, all 6 of these devices would be in one local area network, and a broadcast from any one of them would reach all the others. In VLANs, you add a VLAN tag to the traffic, and so it'll make one VLAN here and another VLAN here. and broadcasts will only go to devices in the same virtual local area network. So port isolation is another issue. If you go to Starbucks and you connect to the wireless network, and somebody else connects to the wireless network, and you run something like an Nmap scan, each of you will see a network that contains only two devices, you and the router. You will not see anybody else because each customer is put on a separate VLAN, so they do not transmit any data from one user to another for privacy. However, you can send traffic directly to this person if they're in, without going through their access point, and they can't control that. All right. So that's port isolation is useful in multi-tenant environments, isolates customers from one another so they don't end up seeing each other. In the early coaxial cable internet, they didn't enforce this, and so if you joined a cable internet, you would go into like my network neighborhood and you'd see all your neighbors there. And if they were sharing files and music, you'd just see it pop up on your screen. That's what this prevents. You're isolated from the other users. Span ports are ports that, called a mirror port. A span port on a switch sends a copy of every packet out the port. So you can put a network device there to record all the traffic. The problem is, if you have, say, 1 gigabit per second at every port, and they're all going at 1 gigabit per second, the span port can't keep up. So it only works for relatively low amounts of traffic. For high amounts of traffic, it may not have enough bandwidth to deliver all the frames. And this is something, I talked to the CEO of Cloudflare, and I saw him talk about this. When Cloudflare bought ports, they wanted like 10 gigabit per second, and they had a 24-port switch. And in Cloudflare data centers, they're handling an enormous amount of traffic. And they found out that an average switch that you buy with 24 ports rated for 10 gigabits, each port speaks the protocol of 10 gigabit Ethernet, but you can't run all 10 ports at 10 gigabit speed. The port can't handle it. There are speed limits inside it. They eventually had to build their own switches because they really wanted to do that. They wanted a switch that had every port on it screaming at full speed, and the ports that are for sale, the switches that are for sale, can't really do that. Anyway, network tap is a device that sees all the traffic on a network. This is what you do. You connect a sniffer to one of those span ports or somewhere else where it can get all the traffic, and you just have a special device just to record all the traffic. So routers run at layer 3, and these take the IP address, which denotes the physical location of your computer, and move things up to the internet and across the network as necessary to get to the physical location. Now, the routers need to know where all the IP addresses are. They might have static routes typed in by a network manager for small networks. For home networks, you just have a default gateway because there's only two choices. You're either on a local area network or you're on the internet. So all it needs to know is one direction to go. For anything that's not on a local network, go out the default gateway. And that's what you have here. So each one of these devices has the default gateway of 192.168.1.1. So they can, if you're trying to send traffic from 192.168.101 to 1.102, you just go directly from here to here. But if you go to anything else that's not on this network, it just sends it to this device, which is the router, that can readdress the packets and send it off on the internet with a real public address. That's how it works in a small network. This is called a stub network, where you have the internet and some devices, but that's it. There's not any other decisions to be made. Now, if you have a more complicated situation, multiple routes, multiple locations, then you use routing protocols. And the point here is, if something happens, like this device goes down, it will automatically notify the other devices to quit sending traffic here and instead send the traffic another way. So a network converges when all the routing protocols, all the routing tables have updated, so it correctly sends traffic and no longer sends traffic to the device that is down. So interior gateway protocols are used by private networks like RIP and OSPF. Exterior gateway protocols are what's used on the internet, and the only one I've ever heard of being used is BGP, Border Gateway Protocol. This is the one used to move things across the internet over large distances, like from one city to another. In the early days, because the routers were very weak and they didn't have much memory and processing power, they used a distance vector routing protocol that didn't really have the whole network map in the router. They would just know AT&T is 2 hops out this port, CCSF is 3 hops out that port. That was all they had. They would know what direction to send it and a very crude measure of how far away it was. This was able to work for small networks when things were slow, but it would have flaws. Like you have routing loops like this, where it would just send things from 101 to 103 to 101 to 103. It would get confused and send traffic the wrong way, and this could persist for several minutes with RIP. So that RIP is old and inefficient, and it only updated every 30 seconds, so it could take minutes to converge, and all that time it's sending packets the wrong direction. So it had stuff like split horizons, so that because another thing could happen with RIP is you could have an update that's good, and then you'd have a bad update that was still coming through with a delay from an old device. So you'd get the routing table fixed, and then it would go bad again. So they had countermeasures to try to stop information from going the wrong way, and it wasn't very effective. Ways to fool Rick. So people hardly use RIP anymore. They use link state routing protocols. Now, each router knows the whole diagram, and they really know how fast every link is. This is, on modern hardware, this is not asking too much, and it's much better than RIP. But of course, you have to have a more powerful processor on the router. But, routers have gotten thousands of times better than in the early days. OSPF is an open source routing protocol used by anybody who wants to use it. That converges very fast, and BGP is the path vector protocol that's used on the internet to move you from one internet service provider to another. So it's quite complicated too, and people make a good living. If you learn to manage BGP, these consultants fly around solving problems for people. It's a real difficult to set up, real important to set up. Good specialty. If you get your CIA or CCNA and you move forward, you can eventually get certified in Border Gateway Protocol, which is a pretty good thing to do for a network engineer. Yeah, so 4H. Is here. All right. All right, so which device runs at layer 3? Those are routers, all right. Good. All right, which device moves a packet from a LAN to the internet? That's a router. That's what they do. You lift it off one local area network to another. It moves it onto the network that goes to your ISP. All right, what protocol uses hop count as a metric? That was RIP. RIP didn't just know the speed of the links. It just counted the number of hops, which is really not the most effective way to choose the best route, to take the one that has less hops instead of the one that's faster. That's one of the many reasons why RIP is very inefficient. And which interior routing protocol converges rapidly? OSPF, Open Shortest Path First. This is an exterior routing protocol that goes across the internet. This is an interior protocol used inside a company, and it converges rapidly. It's a modern one where each router knows the whole network map and can make an intelligent decision of the best path to use. So, all right, we're still okay. All right, and then they got firewalls. The earliest firewalls were just packet filters. They would just, they're stateless, so they would look at traffic and decide if it was on a forbidden port. They would only, it would often allow unwanted traffic through. For example, if you want to be able to ping this device, then they have to let all the echo replies through from every device, because they can only filter things by the port number and the information in the header. Stateful firewalls are more common, and this is what you have on a modern Windows machine, a stateful firewall. So if you turn on the stateful firewall, which comes on automatically when you're not on your home network, in a public network, then if you send a request packet out, it will let the reply through. But if anybody sends you anything without a request, it'll be blocked. This way, your machine can be a client for anything you want, but it can't be a server. So if you want to connect to anything, you're allowed to do that. But if anybody wants to connect to you, like you have file sharing or something turned on, they can't get through. And this is normally what you want. You want to be a client consuming network resources. You don't want to be a server. All right. So proxy firewalls have been around for a while. These break the connection. Instead of doing a SYN/ACK directly to the end device, it's intercepted here and recreated. And the point of this is you can have a table of forbidden sites here. You can say you can't go to games, you can't go to social media, and so on. And so it will decide what you're allowed to get to. You never make a direct connection to anybody.
Exactly, games, video games.
What's that? Yeah, the block games, yeah. Yeah, block whatever you don't like. All right, so application layer can use application layer data like URLs, which is a common case now. They call this deep packet inspection. It's now standard. All right. There are circuit level proxies that run at layer 5, and they can forward many protocols. This is used for things like VPNs, like Tor. Tor uses this to carry all your traffic of every protocol through their special network. And a bastion host, I thought these were extinct, but Microsoft brought them back. You can now get them on Azure to protect your RDP connections. You have a special device which serves in between you and the server. And just the whole point of it is just to be a security screener to filter traffic, because Microsoft found out that if you open remote desktop protocol, port 3389 on the internet, you immediately get flooded with brute force attacks. So it's very dangerous. So they recommend going through a bastion host first, which will filter the incoming traffic and help protect your remote desktop protocol server. So dual homed hosts sit between two networks, and you have to log into the host first, and then you can access the trusted network from there. This is a really old technique, probably not common anymore. Screened hosts, another way, router forces traffic to go to the bastion host, which can access the LAN. And if the bastion host fails, the network is unprotected, so that's one old technique. DMZ, this is still commonly used. In fact, it's used in great extent. You take your network and you break it into segments. So you have a trusted network here where you have to pass through two layers of defense. First, an external firewall that blocks obvious attacks like DDoS attacks. And then you have another firewall here that actually causes you to log in to make sure you really are an employee of the company. And then you get to internal things. But out here, you have public information, like the web server, which you do want the whole world to get to, even if they're not an employee. but you still want to protect it from obvious attacks. So you have, this is called the DMZ, which is a military term, which became popular in the Vietnam War. You'd have a region, in World War I they called it no man's land. You would have this region which neither side claimed, but nobody was allowed to be there. If you went in there, somebody would shoot you. This protected area, that's what demilitarized zone is, where you're not supposed to have any fighting in here.
So it's traditional, it was in Vietnam War.
Yeah, demilitarized zone. This became popular. It was the zone between the fighting armies where nobody was supposed to go. And I think if they have like a white flag and they're surrendering, nobody was supposed to go in there. And you can do it with one firewall. The firewall can have rules that send some traffic here and more strict rules to go there. You don't necessarily need two hardware devices to do it. And in fact, most modern networks have many, many layers. This network, City College has 100 VLANs. So the traffic is sorted into many different categories passing through the network. All right, so a modem translates binary data into analog signals that can go on the phone network. This is pretty much extinct, I think, the old modem, because I don't think anybody has analog phones in America anymore that go down a copper wire. But anyway, they have a more modern cable modem or something. Anyway, or a DSL modem. So DTEs are data terminal equipment. Data circuit terminating equipment is at the ISP's network. And the DMARC is the point where the ISP's responsibility ends, and all the wiring beyond that point is the responsibility of the local client. So the circuit carried by this is synchronous using a clock signal. And so this is not true of a normal local area network. This is true of your connection to the internet if you have something like a T1 line. You have this synchronous signal, and you have to have the clock synchronized at both ends. So in secure communications, there's a lot of different types. We'll talk about authentication protocols, VPNs, and remote access. So the first thing, authentication protocols are a really big deal. How do you figure out who somebody is? Your first way was PAP, where you just send the passwords in clear text. This is a pretty terrible idea. Not only can anybody read it and learn your password, they can just record the packets and replay them to get in. So this is ridiculous, not safe at all. All right. CHAP was the improvement. The server would send a challenge. The user will add the challenge to the password and hash it and send that over the network. And that way they can prove they know the password, but they don't directly send the password over the wire. All right, so this is pretty better. It resists sniffing and replay attacks, but it does mean you have to store plain text passwords on the server so it can do that calculation. 802.1x is the more modern technique, which has a variety of ways to do it. When you connect to the authenticator. The authenticator goes to a server that can tell whether you have the right password, which is running Radius or similar software. This decides whether you've submitted the right credentials and tells the authenticator, and the authenticator either tells you no or it lets you get on the internal network. That's the process of 802.1x authentication, and there are many different protocols supported by this. EAP MD5 was an old one that is not considered secure anymore. LEAP was Cisco's proprietary. It was an attempt to improve WEP, wired equivalent privacy, but it turned out to not be very good. It was also vulnerable and shouldn't be used anymore. EAP Fast is the replacement of LEAP, and this is considered pretty good. And EAP TLS is considered fine. That's the same TLS you use in HTTPS connections. So if you have a more modern version like TLS 1.2 or 1.3, it should be fine. It uses the public key infrastructure. And this one requires certificates on both sides, which is very secure. This was considered costly until a few years ago when Let's Encrypt started handing out free certificates to everybody. So certificates no longer cost any money, but still almost nobody's doing this, although now they're using this thing called passkeys, and I think passkeys are essentially this, a certificate on the client side and one on the server side. TTLS is one where a client can use a password instead of a certificate, and PEEP is protected EAP, similar to the TTLS. So a lot of different versions of protocols. All right, and 4i is here. This is in the way. There. That should be better. There. All right. All right, so what firewall uses only header information? That's a packet filter, the old-fashioned Generation 1 firewalls. Not very effective and not used very much anymore. Which one runs at OSI 5? That's a SOX proxy. Can carry many protocols. All right, which one provides port-based network access control? 802.1x has that property, and this is useful. One problem in security is people would have Ethernet jacks in the wall, and an attacker could just bring in a laptop and plug in. And 802.1x, one of the early things it provided was you could have port-based access control, so only a device with the specific MAC address could plug into that port, and another device would not be accepted. And then you had those cryptographic things added in later. All right, which one is vulnerable and should not be used? Yeah, Leap. Cisco's protocol. You know, Joshua Wright, a famous hacker, wrote a tool called Asleep that would hack into Leap, and Cisco got so mad they published an article saying, what kind of satisfaction does someone get from writing a tool that renders millions of dollars of infrastructure useless? They didn't admit that they'd made a defective product. That was the problem. They thought the attacker that publicized the vulnerability was the problem. And that was really common, you know, until maybe 10 years ago. People felt like ethical hackers should just shut up and not tell anybody, and that would solve the problem. Now we've pretty much grown out of that. Good. Oh, I think we can do another one. Well, let's see, it's 10 minutes to 7. All right, let's take a break until 7, and then we'll carry on. That's probably better.